Good morning. In the last lecture, we discussed definition of an antenna and its radiation mechanism. In today's lecture, which is topic number 2, we are going to discuss pattern of an antenna and its details. So in the previous lecture, when we discussed about the mechanism of radiation of an antenna, the field or power radiated by an antenna is always in a specific shape, and that particular shape in which the quantities such as field or power are radiated as a function of spherical coordinates theta and phi is called as pattern. So pattern is basically defined as a three-dimensional quantity which involves variation in field radiated by an antenna or power radiated by an antenna as a function of spherical coordinates theta and phi. The radiation pattern of an antenna can be three-dimensional or two-dimensional. A usually three-dimensional radiation pattern is represented with this diagram, and details of this radiation pattern includes a lobe. It can be a major lobe or minor lobe. Radiation in this particular example is happening in maximum direction theta equal to 0, and this particular diagram is an example of field pattern. You can see here there are, apart from major lobe, there are side lobes and back lobe, and between two side lobes there is also a null which indicates there is no radiation happening in this direction. So let's now define these terms in detail. So the first example we are taking, the first parameter we are taking is a radiation lobe. A radiation lobe is a portion that indicates the radiation of field or power from an antenna in a region as compared to relatively weak radiation power regions. So thus we can have two kinds of radiation lobes as major lobe and minor lobe. Minor lobe is consisting of, so we have a major lobe and minor lobe. Minor lobe can be in the form of back lobe and side lobe, and major lobe indicates the direction in which the maximum radiation is happening. In this particular figure, which is a two-dimensional radiation pattern diagram, we have shown main lobe in the direction theta equal to 0, and this is a field pattern. The difference between the field pattern and power pattern is the parameter that we are representing. If we are representing E of theta comma phi, here we have taken only one quantity because it's a two-dimensional diagram, and power represents P of theta comma phi. Here we have taken only theta. Now you can see here the term E is taken as e to the suffix n. Let's now define the minor lobe. Minor lobe is radiation pattern's direction in any other direction. It can be in the back direction or side direction other than the intended main lobe. So minor lobes consisting of back lobe and side lobes indicates radiation in directions other than the major lobe. A back lobe is usually opposite to the maximum radiation happening in theta equal to 0 direction. Now let's discuss another point called HPBW, which is called half power beam width. It's half power beam width. Let's draw a radiation pattern diagram again. This is a major lobe and these are minor lobes. As you can see, the diagram is symmetric and representing 4 minor lobes, 1 back lobe and 1 major lobe. At this particular point in the major lobe, there is electric field, normalized value of it is maximum. Half means 1 by root 2, which is 0.707. Half the value of its below there are 2 points. These 2 points, when we join with the center of the coordinate system, we get an angle between these two lines, and that particular angle is indicated as HPBW, half power beam width. Now, as you can see, between two side lobes there is a null at this particular point, and on the other side also. So the nulls can be numbered from the major lobe as null 1, that is first null, second null, on this other side the first null and the second null. If we draw a similar line indicating first null from the major lobe, and if we find out the angle between this, it is termed as FNBW, which is called as the beam width between first nulls. Null is an important parameter in the radiation pattern because it indicates a direction in which this particular antenna at this point is not radiating any electromagnetic field. This can be helpful when there are other antennas in the vicinity of this antenna which are radiating in this direction, so that the interference can be minimized. As you can see in the diagram, the value of HPBW is smaller compared to FNBW. So the relation between HPBW and FNBW is HPBW is half of that of FNBW. So now let's obtain normalized form of radiation pattern. The normalized field radiation En of theta comma phi can be obtained by dividing the value of electric field pattern E of theta comma phi by its maximum value, E max of theta comma phi. Thus, a normalized field pattern is a dimensionless number because this is a ratio of two identical quantities, and half power level occurs at those angles of theta and phi where the value of En of theta comma phi is equal to 1 by root 2, which is 0.707. Now see this example in which an antenna has a field pattern given by E of theta equal to cos square theta. We have considered only one angle parameter, theta, and the value of radiation pattern is cos square theta. Theta is varying between 0 to 90 degrees. To find the HPBW, which is half power beam width occurring at half power, the value of E theta at half power, which is 0.707. So the E of theta, which is 0.707, is equal to cos square theta. If we compute the value of theta, we get it 33 degrees, which is on one side. You can see here, this is the point at which the antenna is placed. This is the radiation pattern, major lobe, and from the maximum value, if we come 3 dB below, the half side we get the angle 33 degrees. So if we multiply it by 2 for computing it on both the sides, we get HPBW as 2 theta, which is 66 degrees. So in this lecture, we discussed pattern, the shape of the pattern, the parameters of radiation pattern of an antenna, such as major lobe, minor lobe, HPBW, FNBW. In the next lecture, we will study beam area or beam solid angle, a technique to measure the area of radiation pattern. Thank you.